Good morning, good afternoon, good evening, everybody. It's Wednesday, it's EMinar Day, and it gives me absolutely great pleasure to introduce or to tell you that today's speaker will be Randy Mackie on geologically consistent inversion of geophysical data, a role for joint inversion. But before I introduce Randy, just quickly go over the upcoming webinars so you can, put them in your calendar. Next week, we have a very special one, and every now and then in this EMinar series, we're going to be introducing talks that are on a much broader theme. We had one a few weeks ago where I talked about publication, and next week we've got one from Nadine Villette on a career in geophysics as a geophysicist. That should be absolutely splendid, and that EMinar is co-sponsored by the Kegs Foundation and by Women Geoscientists in Canada. After that, we have NASA Mecbel's reorganized EMinar. So in a couple of weeks, we'll hear from NASA talking about the code that's certainly the most used by academics worldwide. And then we have Malcolm Sambridge, the winner of the Benno Gutenberg Award for 2020-2021, who'll talk to us more broadly about inversion, optimal transport and geophysical inversion. Following that, we have Andreas Junge, who will introduce a topic that I think needs more attention in our field, and that's anisotropy. And then Jim McNay will talk about unmanned airborne systems and lunar exploration. And then we get back to inversion with Alessandro Santillano talking about another probabilistic method, swarm intelligence. And subsequently, Yasuo Ogawa will talk about imaging fluids in the crust. And Lucy McGregor will finish this season 1 seminar series, giving us her SCG Q1, Q2 distinguished lecture on multi-physics analysis. So just a reminder, you can go on the EMinar webpage, and here's the link, and you can register for any upcoming EMinars or view past ones. And I can probably stop saying this soon. You're probably all very familiar with the fact that this is a Zoom webinar. So the controls you have available are audio settings. You can chat, you can raise your hand, and you can do a question and answer. So if you do that on the fly, Randy might see it and answer your question. Otherwise, the questions will be at the end. Please send your Q&As in the Q&A rather than in the chat. So today we have Randy Mackie, and I've known Randy for a long, long time, and it gives me great pleasure to introduce him. And he's talking about something that we should be doing. We shouldn't stop at our resistivity models, of course, but we should be remembering that we are at heart a type of geologist. We're a geophysicist, and what we want to do is understand the Earth. And so Randy will take us there with his geologically consistent inversion of geophysical data. Randy got his bachelor's in geophysical engineering from Colorado School of Mines and a PhD in geophysics from MIT under the very well-known and respected Ted Madden. He's currently a research geophysicist working for CGG with the multiphysics group in Milan, and his research interests include developing numerical modeling, inversion codes for NT, CSEM, gravity magnetics, and seismic travel times. A lot of that. I'll hand over to Randy. Please share your screen, make yourself visible, and take it away.
Well, thanks, Alan. Hello, everyone. Good afternoon. Good morning. So I'll share my screen. I'll turn off my video, and because I find that distracting, and I'll try to turn it back on at the end of the seminar. So. Go, let's see, screen 2 and share. All right, are you seeing that, Alan?
Yeah, good to go, Randy.
Okay, so thank you everyone for being here. As Alan said, thank you for that kind introduction. And as Alan said, I'm going to be talking about joint inversion today. I work with CGG Geoscience with the multi-physics imaging group in Milan, Italy, and I'd be remiss not to acknowledge all my colleagues in the group I work with at CGG, who I've listed here on this slide. This talk, especially the examples I'll show later, is really a collaborative effort, and without the help of my colleagues here, I couldn't do half the things I'm able to do, so I want to acknowledge their contributions. So here's a simple outline of the talk, broken broadly into 3 parts. Want to give you, I hope to motivate a little bit the utility of joint inversion. Then I'm going to spend some time on an overview of various joint inversion approaches. And then I will spend some time showing some examples that we've worked on from geothermal and the oil and gas sectors. I hope will demonstrate the benefits of joint inversion. So it seems reasonable to expect that by combining data sets in multiple data sets into our interpretation, that the resulting model would be more reliable and more reasonable. Well, conceptually, this is because different data sets have different sensitivity kernels. That is, they're sensitive to different parts of the subsurface. And we hope that by using data with complementary sensitivities, we can improve the fidelity of the resulting Earth model. So for example, one such example is combining marine magnetotelluric and marine controlled source EM data. And that's because in these type of marine environments, because of the sedimentary layering, the resistivity modeling is anisotropic, and we have to model that anisotropy. But the magnetotelluric data are more sensitive to the horizontal conductivity and insensitive to the vertical conductivity. And meanwhile, the controlled source EM is more sensitive to the vertical conductivity compared to the horizontal conductivity. So I take a very broad and holistic view of joint inversion, in which I include not only inverting more than one particular type of data set, but also including other available geological and petrophysical data. Okay, so these are some figures I've taken from the CGG website that show the current state of the art for seismic reflection. I think the level of detail is really quite amazing, and it continues to prove every year. These clearly show geology and geological processes in great detail, and I think you'd be hard-pressed to say that these are not representative of geological structure. So that's sort of what we're up against at one end of the geophysical spectrum. Meanwhile, let's see over in the MT world how we're doing. Here's a structural model from a foothills type of geology, and let me just get my pointer. From a foothills type of geology, where there's complex overturned beds and faulting, and it's difficult to collect good seismic data here, and so MT data is often collected. If you just invert MT data taken in these types of areas, it produces nice blobs that I would argue are not particularly geological nor particularly useful, because the exploration companies, they're not interested in where blobs are. They're interested in where to drill and at what depths they're going to hit certain formations. Well, you can, in these situations, invert the data while also coupling in other information like the structural model, the gradient fields from the structural model, and then you get something, a result like this, which I think is more geologically reasonable and matches more closely the geology in the area. I think it's a bit unfair to compare seismic reflection to MT because the physics are very different, of course. In one case, we have wave propagation, and in the other case, we have diffusion. So the resolution that's possible from each method is not the same. And I'm not suggesting that we can resolve fine scale detail from our MT data alone, like I showed here. But I think we can do better than the blobs that don't correlate particularly well to known geology, or where there's little correlation between different geophysical data sets. And I think that joint inversion and coupling in external geological information offers us a path to the increased fidelity of our model. Here's an example from the Darajat geothermal field, and I'll talk about this in more detail a little later, but I just want to give it in advance to promote the utility of joint inversion. On the left-hand column are the single domain inversions In the top row are the models, the resistivity models from inverting magnetotelluric data, and on the bottom are the density models from inverting gravity data. And on the right-hand side are the results from joint inversion, jointly inverting the magnetotelluric data and the gravity data, and also coupling in an external geologic information, that's a porosity model. So you see in the single domain inversions, there's not much correlation between the two methods. And this purple line is the top of the reservoir, the top of the geothermal reservoir. MT by itself does a pretty good job, but you see that the joint inversion clearly has more consistent interpretation between the two results and to the external information. More and more we're getting, we get multiple data sets to interpret, and joint multiphysics inversions and interpretation are becoming the norm rather than the exception. It's rare that you have just one data set. It's rare that you just have magnetotellurics. There's often gravity and magnetics and seismic. And so I think it behooves us to use all those data sets and use them in our interpretations. Okay, so let's just get right into it. Here we're going to pose inversion as a minimization of, in the normal way, the standard way is the minimization of an objective function, which is the sum of two parts. We have a data misfit part, which is given by this, and a model smoothness or model regularization part given by this second term. And the normal way to solve these is by some gradient-based method like Gauss-Newton, quasi-Newton, or nonlinear conjugate gradient. And I do want to say and point out to my my predecessors in this EMinar series. So all the concepts of inversion that were discussed in earlier talks, especially in Doug Oldenburg's and Colin's talk on inversion, apply here, and we can build on that. Okay, so if in the example that I gave earlier of magnetotellurics and marine controlled source EM, the underlying property model is just a single property, that is electrical resistivity. So in that case, we have two different types of data that we're inverting, and we augment the objective function with an additional data misfit term. And for the moment, I'm just keeping this simple, and I'm ignoring any data weighting that that might need to be applied, and I'll talk about that a bit later. Okay, an example of inverting magnetotellurics and gravity, for example, the example I showed earlier from the Darajat geothermal field. In this case, we have the two data misfit terms, one from magnetotellurics, one from gravity, and then now because we have two underlying properties, we have resistivity and density, each has their own model regularization term, but now we have this coupling term, and this coupling term is really the critical link that links together the density and the resistivity models, and we're going to talk about that in more detail in just a minute. And finally, I want to mention, finally, we want to go a little bit more and add in external data, and we'll couple to external models or geology or petrophysical data, and that's an additional coupling term here. Okay, so I want to spend about one slide on several of the most used coupling methods, and hopefully just give you a feel for a general understanding for what these methods are and how they're used. I'll start with structural coupling methods, and cross gradients is probably one of the most widely used approaches for carrying out joint inversions. And this is because it doesn't assume any intrinsic link between model properties, and quite useful for when there are no intrinsic link between model properties. Rather, it tries to impose structural similarity between two models. It was proposed by Gallardo and Mayhew back in 2003, and then a series of other papers. And the idea is that by adding a term like this to as your coupling term to the objective function, that you can enforce model similarity. And this is just the L2 norm of the cross gradients between the two models. Well, the cross gradient term is 0 if the gradients are parallel or anti-parallel, and that is, it doesn't require them to be in the same direction, or if one gradient has a length of 0. And this is an example I've pulled out from the Gallardo and Mayhew paper in 2003. It was a near surface exploration problem. The top was the velocity, and the bottom is a resistivity model, and you can see the similarity in the two models. So this was, okay, by no means was this the first structural model similarity link that was proposed. In fact, earlier, Eldad Haber and Doug Oldenburg in 1997 had proposed using the zero crossing of curvature. There are other trigonometric and normalized gradient functions that can be used. I'm not listing them all here. There's also a variation of the cross gradient method called summative gradients, in which if you know in advance that you want the gradients to be in the same direction or in the opposite direction, you can enforce that, and that's a stronger link than cross gradients, which doesn't care what direction, as long as you're parallel. That's the only thing that matters. Well, cross gradients, as I mentioned, can be used to promote model similarity between two different model domains. It can also be used to couple in structural information from other places and steer the inversion. So if you have surface geology like strikes and dips, that can be coupled in. If you have a geological model, you can use the gradient field from that to guide an inversion. If you have an external physical model like porosity or something else, that can be coupled in. And also, if you have a seismic reflection volume, the gradient field from that can be used to guide an inversion. Okay, another type of structural link is called mutual information. This is a distance metric that is used in the medical image field. And it's given by this formula here, where the P's are probability density functions. The expression can also be rewritten equivalently in terms of the entropy of random variables, which is the formula Max had in his talk from a few months ago. And before I saw Max's talk, I thought this paper from Andelesi and Jones was the only example in the geophysical literature. But Max is currently using this, and I encourage you to go and look at his talk if you haven't, because I think the examples he shows are very good there. In this case, from this paper, they were inverting magnetotelluric data for electrical conductivity, for anisotropic electrical conductivity structure, which you see here. And as a reference model, they're using a reference model from seismic anisotropy. And so the idea was to make sure that the electrical anisotropy and the seismic anisotropy were similar. So this seems to be a stronger link than cross gradients, and I'm very happy that to see that Max is carrying on and using this. Okay, so moving on from structural links, look at the situation in which we might have external geologic, petrophysical, well log data that we can use to constrain an inversion. And here I've liberally taken a figure from Max's review paper in 2017, where he was looking at the difference in two different studies. They were using well log information from the same well, the Rugden well and the Faroe Shetland Islands, as a way to constrain their interpretation. Now in this, in the earlier work in 2016, so the idea is from that well measurements of velocity and resistivity, and you can plot them in these cross plots, and you can derive some sort of an empirical relationship between the two physical parameters. In this study, they were using that empirical relationship to convert the results of a magnetotelluric and CSEM inversion to a seismic velocity model, and then they used that model for migration, and they showed that improved the migration image compared to the normal approach. In the later study of 2017, they use these empirical parameter relationships to penalize deviations from the rock parameter relationships in their joint inversion. It was inversion of gravity, magnetotellurics, and seismic velocity. The problems, this is a very simple and straightforward approach, but the problem, of course, is that these relationships are only approximate, and you see a lot of scatter around these empirical relationships. Well, moving beyond the simple parameter relationships, but also where we might have information that cluster in some form, we can use the concept of fuzzy C-means clustering. And it's a very similar concept. If you have a cross plot like this, one property plotted against the other, and if they cluster in some way, then we can use that information to guide the inversion into a more petrophysically or geologically reasonable model. The idea behind fuzzy C-means clustering is to add a coupling term, which is something similar to this, where U is called the membership value. It's sort of like a probability that a particular model cell belongs to a particular cluster. Q controls the fuzziness of the membership values and is usually set to 2. D is a distance measure, and in the simplest case, like here, this model's circular clusters is just simply the distance of a model parameter X away from some cluster value V. There are a lot of papers by Jia-Sun and Yagao Li and their group, Yagao Li's group at Colorado School of Mines, and I've just taken this example from the paper in 2016. This was a synthetic example. They were synthesizing seismic and gravity joint inversion. They had crosswell seismic, so they synthesized crosswell seismic across the synthetic model. They also had synthetic gravity measurements at the top and along the sides. And so in this column, we're showing the results. They're showing the results of the single domain inversions, and they actually do a pretty reasonable job. Of course, it helps having the crosswell aspect of it. But if you look at the cross plot of the density versus the slowness at the bottom, these red dots specify the true values in the synthetic model. But you see there's quite a scatter of the values and don't really get close to the true values over here, including this coupling term in the inversion, and then carrying out a joint inversion, they obtain a much better result, sharper results, and you can see the clustering around the true values. So this distance measure models circular clusters, but there are variations, different distance measures that will allow you to model elliptical clusters, and then linear clusters are just sort of like a very long, skinny elliptical cluster. Another interesting approach to add in petrophysical and geological data to an inversion is by use of a Gaussian mixture model. This was mentioned by Doug Oldenburg towards the end of his webinar. This comes from his student in his group. And what's nice about it is that it can be used with existing inversion codes by quite simply adding instead of a model smallness term that's related to the distance away from some a priori model, you add a model smallness term that's now related to a Gaussian mixture model, in which the geologic unit's physical properties are represented by a Gaussian distribution. And so in this way, it introduces uncertainty to the petrophysical and geological data. And the algorithm proceeds quite simply by sequentially solving the three problems here, starting with geophysical inversion, then petrophysical characterization, geological identification, and then it just iterates on this until it's converged to a solution. So here's an example at the right, which I've taken from their 2019 paper. This was a simple synthetic model for DC resistivity. The top row is showing the results for the standard Tikhonov smoothest model style of inversion with no additional constraints, and it doesn't do that bad of a job. On the right is a histogram of the values of that, of the resistivity values from that model. And the true synthetic model is given by the black line. And the bottom row is the result of then adding in adding into the inversion the true petrophysical distribution. And you see you do a much better job of resolving the true resistivity and matching the histogram. So continuing on the petrophysical links in hydrocarbon exploration, it's important to estimate reservoir parameters like the oil, water, and gas saturation and porosity. And seismic data and seismic attributes are not particularly sensitive to the gas saturation, for example, but electrical resistivity is through the link to water saturation and via Archie's law, which I've put here. So therefore, it's reasonable that we can better determine these parameters through a joint petrophysically linked inversion. And the idea here, this is an example I took from Mike Hoverston's paper in 2006. There's other papers, for example, Ari Abubakar in 2012, and the Schlumberger group spend a lot of time on petrophysical inversions. So the idea is that you're going to jointly invert like marine controlled source EM data and seismic data. Here's amplitude versus angle of incidence. And in some target zone in the reservoir, you want to, instead of parameterizing the model in terms of electric resistivity and seismic velocity, our model parameters will be those parameters that we're really interested in, which is water saturation, gas saturation, oil saturation, and porosity. Okay, so in order to do that, though, you have to have some link between those parameters and what we and electrical conductivity and seismic velocity. In the case of on the electrical side, we can use Archie's law as a link between those various properties. On the seismic side, there's other various rock property models like the Gassman fluid substitution model that exist and can be used. So I didn't put those here, but I refer you to these papers if you're interested. And here, this is just a reminder that, in this zone, okay, when we have to take the gradient of our objective function, now we just use the chain rule to get it. And the first part of these terms, so theta in this paper, theta is the cost function. And to take the gradient with respect to the gas saturation, for example, we just use the chain rule. And these are the normal, the first part of the terms are the normal values that we get from our physics modeling codes. And then the second parts come from our rock property models. And so that's where the approximation comes in. Here is an example I've taken from Mike Hoverston's paper showing the result of the joint inversion for the petrophysical parameters in this zone. The true values are given by the red line here, and the inversion started from uniform values, and you can see the inverted values in the blue line match quite well. And they've also tried to estimate some uncertainty to the results. They point out that the results of the joint inversion are improved over the individual inversion, and it's these values which they're ultimately interested in, not values of electrical conductivity or seismic velocity. Okay, I want to mention Gramian constraints were introduced by Stanoff in his group. And this is based on minimizing the determinant of the Gram matrix for the system of different model parameters. Here I'm showing the Gram matrix using structural information. That's the gradients of the two model fields. And it's clear that the determinant is a measure of how parallel the gradients is, because when the determinant's 0, that means the gradient fields are parallel. This is an example I've taken from the Jorgensen and Stanoff paper, 2019, where they were inverting and interpreting magnetotelluric and gravity data. And this is a synthetic model they created to show the utility of this method. On the left is the true synthetic model. This is density on the upper row and resistivity on the bottom row. The middle column show the results of the single domain inversions, which you know, don't do that bad of a job, but do not completely capture the reality. And then the last column shows the results of the joint inversion when you use the Gramian constraint to tie the model parameters together and enforce structural similarity. And finally, I was talking earlier about image-guided inversion. So you can use external information to guide an inversion into a result that is more geologically reasonable. This is the example I showed before where I used external gradient fields that came from a structural model to guide the inversion. And other approaches take that information and use it to modify the regularization parameters. And this is an example from this paper of Geol and al. In 2014. Okay, so let's go back to looking at the objective function. And this time, I'm making explicit that you have weights in front of each of these terms. So we're faced with the usual situation where we have to estimate these weights somehow. And a lot of the tools that we already have carry along also into the joint inversion case. The tools that were talked about in Doug's talk and Colin's talk, for example, like L-curve analysis for determining the model weights, carry over here as well. Data weights are one thing that you have to worry about in joint inversions that you don't have to worry about in single domain inversions. And the reason is this: if the idea behind the whole joint inversion, I think, is more or less we want the data from two different data sets to have roughly similar influence on the inversion, which is why we're including different data sets in the inversion. But if one data set had a lot of data points compared to the other one, then then this data misfit function is going to be much larger in that case compared to the other one. It will overwhelm the inversion, and the inversion will spend most of its time trying to fit that data compared to the second data. So you have to equalize them in some fashion. The other thing you have to think about is maybe they have different, they see the Earth differently, okay? And they have different impacts on the model. And so you have to kind of balance that in some way. There's really no right way to do this, in my opinion. I think there's many different approaches, and I've listed several of those approaches here. You could just set some constant values and then run your inversion. I think a reasonable starting point is to base it on the number of data points, because we want each objective function to have more or less similar weight on the inversion. Other people will base the values on the norms of the gradients or the sensitivity values. L-curve analysis applies here as well. You can just run many inversions with different values and take a look at what you get. And I think there's great value in doing that. I always recommend doing lots of inversions with many different trade-off parameters, because it gives you a good sense of what your data are capable of resolving and at what point you start to see geologic or geologic noise or noise affecting the inversion models. Some people like to dynamically determine the values during the inversion based on some cooling schedule, and that is looking at the misfit values and rate of change and things like that. They come up with a scheme to automatically change it so that you don't have to try to do that yourself. I think an interesting approach, I saw a talk a couple of years ago by Joe Capriati and Yao Li, in which they included those values to be determined as parameters to be determined during the inversion. I think is an interesting approach. I think, as I said before, I think it's important to always run lots of inversions. You know, my old advisor, Ted Madden, said that inversion was as much of an art form as anything else. And I think that's still true. You really, you know, there's really no right or wrong way to do it. Different data sets have different information content, and it's always takes some effort to get a good balance between the different data that you're trying to jointly invert. Okay, so you might hear usually we have our joint our objective function, which includes multiple things, multiple data, misfit terms, model regularization terms, coupling terms. If you just try to minimize that all at once, that's called a simultaneous joint inversion. All the tools from single domain inversion carry over. You have to compute gradients, Hessians and things, and you just do that for each one. Because of the problem that comes about trying to determine the right balance of data weights, some people will try to minimize that objective function in a sequential manner, and you'll hear the term sequential joint inversion, where you alternate single domain inversions. So for example, if you're inverting magnetotelluric data and gravity data, you do some number of iterations of magnetotelluric data, and then you use that model as a reference model for gravity inversion, like coupled in using cross gradients, and you just iterate until you get to until you've minimized this objective function. Some people will use the term cooperative joint inversion also for sequential joint inversion. I like to think of it as when you're trying to couple in fixed external information. And finally, before I get to some examples, I just want to, in this very conceptual way, talk about what we're actually doing. So just consider a very simple example where you might have the situation we're trying to invert electromagnetic data and seismic data. And you can rewrite it instead of all the individual terms as a sum of two different objective functions. And I'm ignoring for now any coupling between them. It's probably very unlikely that you can find a model M that simultaneously minimizes both functions. That's because if we conceptually draw the EM objective function like this, the minimum is here, and the seismic objective function, the minimum would be here. And so really when we're doing a joint inversion, what we're trying to do is not find one of these minimum, but actually find the minimum of the overlap. And this is also why joint functions often take many more iterations, because the objective function is not so nice as it is in the case of single domain inversions. Well, there's a whole field of multi-objective function optimization that I'm not, other than this paper by Semerchi and others in 2014, I'm not aware of really us in the geophysical community using, but I think there's a lot of potential there for modifying the approaches we use to solve these minimization problems. So I think this is an interesting area that could use some bright young student to look into and bring into the geophysical world. All right, so with that overview, I hope that kind of gives you an overview of the different coupling approaches and joint inversion, some of the issues. I'm just going to show some examples now from the work we've done. First from geothermal area, and I apologize if some of you have seen this work before, but I think it's a very illustrative and interesting example. So I'll be discussing both volcanic and volcanic-hosted and fault-controlled geothermal systems. And on this slide, I'm showing conceptual models of these two. On the left is a conceptual model of a volcanic-hosted system, a conventional permeable 250 to 350 degree geothermal reservoir. And here, thermal buoyancy causes water to flow upwards against gravity, and it drags the isotherms with it. The electrical resistivity here is controlled primarily by conduction in saline interconnected pore fluids and in clay mineralogy. Oops, I don't know why that happened. In clay mineralogy, the low resistivity clay cap on top of the reservoir is associated with low temperature clay alteration in the presence of smectite, which is conductive. Well, deeper in the reservoir, it's hotter, but it's more resistive because the effective porosity is not high enough to generate low bulk resistivities. In the right, this conceptual model of a fault-controlled system, the upflow is primarily along faults. There can still be capped by clays and sedimentary units that come both from sedimentary processes and geothermal processes. Okay, so there are three primary methods used to image geothermal fields. That's magnetotellurics, gravity, and microearthquakes. Magnetotellurics is used because the conductive clay cap over the more resistive reservoir is well suited to being imaged by MT, being an inductive method. It images the clay cap very nicely. Gravity data relate to the bulk density, and so that's primarily a function of the rock matrix density and the porosity, and so it's expected to be denser deeper in the reservoir. In fault-controlled systems, the gravity can also give good structural control. Once a field is producing, then that generates microearthquakes that can then be used. We can model microearthquakes and get information about pressure changes and fluid movement. Both microearthquake analysis and gravity analysis are often done over time, repeat surveys, so you can get look at temporal changes and how the field is changing as production carries on. So Derajat is a vapor-dominated geothermal field in West Java, Indonesia. And it's one of the best studied geothermal fields in the world, with many publications on the geology, geophysics, and geochemistry. Over 50 wells have been drilled, and the first production was a 55 megawatt power plant in 1994 with increased production later. It's currently run by Star Energy. So these two maps show the geophysical data sets that we had to use for the analysis here. On the left is a topographic map of the study area. And the symbols, the blue symbols, are the MT stations. There are two campaigns, a total of 84 stations. Some data were collected in 1996 and the rest in 2004. These were broadband MT sites. The data collected in 1996 went from 100 hertz down to 1,000 seconds. And then the data from 2004, they were able to collect data up to 10,000 hertz. There are a total of 538 gravity stations shown by the reddish or pink symbols. On the right is a color contour of the microearthquake, the MEQ event density. There were 21 receivers shown by the green symbols. These were 3-component seismic receivers buried about 1 meter below the ground. And for this analysis, data from over 10 years, from 2005 to 2015, were used. There were a total of 5,100 MEQ events. From that, we were able to extract about 33,000 P and S wave arrival times. You can see MEQ only span a small portion of the study area. Okay, so we ran a suite of inversions, including single domain inversions, joint domain inversions, and then joint domain inversions, and then coupling in external geologic data in the form of a porosity model. Today, I'm only going to be able, I only have time to show you the results of the MT and gravity joint inversions. Okay, so I showed this before. This was the east-west profile of single domain inversions, starting from homogeneous half spaces. For the MT inversions, we set error floors to be 5% of the impedance, and for gravity, 0.5 milligauss. This is the east to west profiles, and on this column, the north to south profile. So you can note, this purplish line here is the projected top of the reservoir. And you can see that the MT does a pretty good job of imaging the details of the geothermal system by itself, including the more conductive clay cap over the more resistive reservoir. In the single domain inversion here, the gravity by itself reveals higher density, but in the core area, but it's poorly resolved and doesn't really match the known geology. But that's not surprising, since we know gravity on its own is pretty much depth insensitive. Okay, so the next step was to do a joint inversion using a cross gradient link between resistivity and density. So here are the single domain inversions again, and then on the right-hand side is a result of a joint inversion, but then just using a cross gradient link between the density and the electric resistivity. So on this bottom slide is the density, and the contours are from the resistivity model. So you can see that there's a strong correlation between density and resistivity. The changes are predominantly in the density model. There are more minor changes in the resistivity model. Okay, so next we wanted to add in a link to an external reference model. And just to remind you that the cost function is then augmented in addition to the data misfits and the model smoothing, and then a cross gradient link between the properties. You can add in a link to the external model that we wish to link into the inversion, and that's this term here. We were provided a porosity model for Darajat that was by the client, which was generated based on a wide range of data, input data, including drill cores and cuttings and surface sample analysis, well logs, geologic mapping, geophysical data. The lithological units were classified into petrophysical groups, and each group was assigned a specific porosity value that was estimated from helium saturation studies of core samples. On the left is the porosity model, the original porosity model that was provided to us as a GoCAD S-grid, and on the right is the porosity model after we painted it onto the inversion mesh and smoothed it. So when you're doing a cross gradient link to an external reference model, you have to smooth it because you really need gradients everywhere in the model in order for it to work. So here are the results of doing the joint inversion between MT and gravity. This is what I showed you earlier. So this is using a cross gradient link between resistivity and density, and also a link to the external porosity model. The contours on both are the contours from the porosity model, so you can see the model similarity not only between resistivity and density, but to the external porosity model. Now we did in this, so we started this inversion from the previous result, but we did edit the density values, and instead of having this high density, higher, we inserted a smooth gradient to the higher density deeper in the model, which was considered to be more geologically reasonable. We also reduced the coupling term between resistivity and density by a factor of 3, which is why the misfits are now a little bit lower than they were before. So this clearly illustrates the linking between all three properties involved: resistivity, the density, and the external porosity model. Well, you know, a key measure of how good we do is, you know, how will they represent the actual subsurface conditions, right? So, you know, interpretations of geothermal resource potential often come in targeting, more wells. Typically, they rely heavily on resistivity models from 1D, 2D, and 3D interpretations. In this figure, I'm showing the model resistivities at a depth of 400 meters below the surface from the inversion, which was just on the previous slide. And I'm also showing the thick bluish contours here are the methylene blue percentages that are come from well cuttings. Well, methylene blue is a organic dye that shows high selectivity for absorption by smectite clays, and so higher numbers indicate higher amounts of smectite clay and lower resistivity. So this depth slice is within the clay cap for the reservoir, and so you can see a very good correlation between the higher methylene blue numbers, which are these darker blue lines here, and the lower resistivity that comes out of the joint inversion. There are other indicators not shown here in addition to the methylene blue that indicate the improvement in the interpretation using the joint inversion approach compared to normal workflows not utilizing joint inversion. Okay, so next I want to move to quickly to another geothermal example. This time it's in Sumatra, which is an example of a Gramian-hosted system. So these two figures are taken from this paper I've listed here, where they're trying to point out the link between the volcanic centers and the polar part basins next to them. On the right is a zooming into the Sorkhon-Merapi volcanic cluster here and the polar part basin next to it. This is an example we're going to show. But before we get to the real data, we carried out some simulations based on the type of geology that we expect to see here. So we created a synthetic model using real topography, and this has about 1,100 meters of elevation change from the highest point over here to the lowest points here. And the synthetic model borrows from both types of conceptual models that we talked about earlier, both Gramian, fault controlled, and volcanic. And over the, so we have the volcanic, we have the Gramian structure here, and over the area where the topography is higher, we have a more volcanic type of system. And this is shown on this right side. This is a map of the base of the conductor. So we generated synthetic data, synthetic MT data at each of these white spheres spaced a kilometer apart, and gravity every 500 meters at the pink symbols. We inserted Gramian faults. Oops. We inserted Gramian faults down to about 3 kilometers depth at a steep dip. Okay, here we're showing the results of an integrated interpretation of MT and gravity, but done in 2 different ways. I talked earlier about cooperative inversions. And so the models that we're showing in each of these is the density model. On the left is the interpretation workflow was a cooperative workflow, and that is that we used the result of the MT, a single domain MT inversion as a reference model for the gravity, since gravity is more non-unique and depth insensitive and has more problems. And on the right is the results of a simultaneous joint inversion of MT and gravity. On the top row, the contours are from the MT model, the corresponding MT model. On this side for this simultaneous joint inversion, over on the left side for the cooperative joint inversion. So you can see this, the model similarity between gravity and resistivity. Sorry about that. On the bottom, we're plotting the contours for the true density from the synthetic model. So it's clear that both methods do a good job at recovering the density model, but I think probably the sequential joint inversion here does a better job, especially at recovering the low density part in the Gramian zone. Okay, now to move to the real data case of Sork-Merapi. On the left is a topographic map of the Sork-Merapi geothermal area. Also, the plotting symbols where the MT stations are located, which are the black inverted triangles, gravity sites, the pink symbols, and the wells, various wells and well traces also shown. On the right is the complete Bouguer gravity map using a reduction density of 2.4 grams per cc. Also, the fault trace, the inferred fault traces of this Gramian zone were picked from structural mapping and as well as tracing gravity gradient maximum. We're going to be showing results of, sorry about that. We're going to be showing the results of inversions along this profile. So here are the inversion results of doing 3D inversion of the magnetotelluric and gravity data. On the top row are the single domain inversions. The left-hand column are the resistivity models from MT, and the right are the density models from gravity. The single domain inversions image the central Gramian area pretty well, but everything is sort of smooth and fuzzy. If we jointly invert MT and gravity using a cross gradient link between them, we sharpen things up quite a bit, and we do a better job of getting structural similarity between the density and resistivity, especially in the Gramian area and off to the east over in the, so you get good correlation between the low conductivity and low density sediments, which is geologically reasonable. And finally, you know, we can do the joint inversion, but then we can put in a priori fault tears where we put in breaks in the regularization. And this is much more geologically reasonable thing to do. Sorry about that, I'm not sure why that keeps happening. And in this case, you see it sharpens things up even more in the Gramian area. Okay, here's a close-up of the Gramian area, the electrical resistivity model, and we're also plotting the well that comes down and goes across here, and as well as the methylene blue values again. Recall the methylene blue is an indicator of the amount of clay in the electrical, and therefore an indicator of the electrical resistivity. Color coded here, and you can see it changes across the fault, and the inferred fault location was here, and also plotted as a line plot. So this was this well information was provided after the fact, and so you can see there's good correlation between the 3D inversion and the methylene blue values. There's a positive indicators to the validity of the inversion result. Okay, and then lastly and quickly, I want to talk about something that comes from the oil and gas industry, and this is the situation we often have when in like offshore exploration, where we might have marine controlled CSEM and MT, and there's often quite good seismic reflection data as well. And how can we use that information in our interpretations? Well, one potential way to do that is we can use interpreted seismic horizons to create operating models. We have to figure out some value of electrical resistivity, use it between the interfaces that might come from well logs, for example. We could also have tear surfaces to impose sharp discontinuities. But there's a problem with that, is that in areas where there's complicated geology, those interpreted seismic sections can have multiple values in Z, especially across fault zones and overturned geology. It requires you to come up with some reasonable value for the electrical resistivity between layers, which might necessitate interpolation between distant wells. It's a difficult proposition to do. So instead, we propose that you can use the 3D seismic image directly. Skip the whole business of interpreting horizons and units and just use a cross gradient constraint to promote structural consistency between the EM and seismic image. The only problem though is that there's an issue of scale. The typical seismic reflection volume might have, down to 6 meters or less horizontal and 2 to 4 meters vertically, where in our EM models, they're typically much bigger, a couple hundred meters horizontally and 10 to 100 meters vertically. So we can solve that issue by using the structure tensor. We'll say, well, any fine scale variations below the EM model cell sizes are not relevant to the problem. But we still need to average the gradients within an EM model cell to get something that we can use in our EM inversion. So we use the structure tensor where these values I are just simple gradients that come from the seismic reflection volume. And then we'll just average over each EM model cell. If you carry out an eigenvector analysis of that tensor, then that represents the principal directions and can be used in an inversion. And we use that again by coupling that gradient field information from the seismic reflection volume in this way. So in a normal cross gradient inversion, you have two different model properties, but now we're just using this fixed gradient field from the seismic volume in the inversion. So we've applied this in many areas. This is an example from fold thrust belt in Saba. It was a large CSEM and MT survey. But for this particular study, we used a subset of the data, 63 sites of CSEM data, 26 tow lines, offsets out to about 12 kilometers for the long period data. And we interpreted both EX and EY from low frequency of 0.125 hertz to 2.5 hertz. The CSEM stations that were used are in blue here. We also had 398 MT sites shown in red. Good quality data between 1 and 1,000 seconds. We had a seismic reflection volume that covered part of this area it was full waveform inversion, migrated, Kirchhoff post-stack depth migrated volume. And this is showing the slice from that seismic volume along this profile. And these are the interpreted seismic sections that were given to us. Well, we carried out a sequence of MT only, CSEM only, and joint MT CSEM inverse modeling using, and I should point out here again, so we're inverting for anisotropic electrical conductivity, both the horizontal and the vertical component. On the left is the result of the unconstrained MT inversion showing usual blobs that are associated with the core of the thrusted and overturned sedimentary layers. On the top, however, is a cross section showing the vertical resistivity that comes from a joint MT and CSEM inversion, and then using the cross gradient link to that seismic reflection volume. The interpreted seismic horizons are shown here, but they weren't actually used in the inversion. It's just to show how this type of image guided inversion actually is structurally conformal to the external seismic data. And then finally on the bottom here is the co-rendering the electrical resistivity over the seismic data. Okay, so that brings me to the conclusions, and I think the goal is we always want to add in as much data as we can into our inversions, into our interpretations. There's always a lot of data available, and we can incorporate not only geophysical data, but any geological data that we have with the goal of getting a geologically consistent and reliable model. So thank you. Thank you for being here and listening to the talk. And I'll be happy to. quick questions.
Well, thank you very much, Randy. I'm going to clap on behalf of your huge audience. Yeah, absolutely fabulous, and impressed on us the need to think beyond the conductivity model. So I'm going to take the prerogative of being the host here and ask you very first question, and that was if you could bring up the cross gradient density model. Go back about 10 slides or so. Yeah, a bit more, back. Yeah, back. There, that one. Yeah, it struck me that there's a huge difference. There must be a huge difference in the gravity response between the bottom left and bottom right models.
No, not really, because remember, gravity is like an integral of the mass underneath you, and it's just distributed differently. Here you have more close to the surface, and here you have.
Yeah, but it's laterally moved as well.
It's laterally moved a little bit, but it's the integral of the mass under.
Yeah.
The misfit's a little higher. It is a little higher here than it is here. It's true.
What I'd be interested in is, Randy, I'm always focused on how the misfit is distributed.
Right.
Yeah, and I wonder whether the misfit would be distributed differently for those two.
That's a good question. Here in this final, the misfit's lower than the first one. When you do these joint inversions and you link them, and we're promoting structural similarity, and as I pointed out in the one slide, it's difficult to find a model that simultaneously minimizes both. And so we often find, when we get these models that are more structurally similar, but often at slightly higher misfit. But your question about the distribution is a valid question. Important to look at, I agree.
So we have the first question in from Syed Mohammed Abtabi Furosh, and Syed is often the very first out of the blocks. Thank you, Syed. I'm going to read out your question so that it's in the record for the people who want to view this later. Thanks a lot for your exciting presentation. A basic question: why is MT more sensitive to horizontal conductivity, whereas CSEM is more sensitive to vertical conductivity? And did you impose a structure tensor in cross gradient to overcome this problem?
So MT is, they're both inductive methods, but we know MT, what happens are electric currents are induced primarily in electrically conductive features, right? So in these conductive clay caps, and the fields are primarily horizontal. So it's just a fact. That's just the fact of the physics, is that you're just not going to be that sensitive to resistive features for MT. In CSEM, the situation is a little different because you have vertical current flow that has to cross those resistive features, and so that's the difference. In one case, in MT, you're inducing fields and not necessarily the currents stay in the electrically conductive zones and don't cross the resistors. In the other case, they do. So that's in a nutshell, that's why that happens. And what was the second part of the question?
And did you impose the structure tensor in the cross gradient?
Oh, so yeah. So in the inversion of MT and CSEM data, where you're inverting for electrical for the anisotropic conductivity, yes, we impose the different ways you can do it, but in this case, we used a cross gradient link between the horizontal conductivity and the vertical conductivity, as well as a link between one of those and the seismic reflection volume.
Yeah, great. I mean, absolutely right about the physics, Randy. It's the difference between poloidal and toroidal current flow systems.
Right.
Yeah. Garrett Kramer. Hi, Garrett. Good to see you on these. Hi, Garrett. Perhaps I missed in your last example. I'm confused what the gradient of the seismic KPSDM image is. What property are you taking the gradient of to minimize the cross product with R? The interval velocity?
So these are just gradients in, well, that's a good question. We take gradients of something, that's a good question. I'll have to, I can't tell you off the top of my head since I'll tell you.
Yeah, thanks, Garrett.
Sorry, Garrett.
Yeah, don't ask another question. Yeah, I'm sure Randy will get back to you, Garrett. Daniela,
it's an amplitude, right? The seismic flux.
Yeah, it must be gradient of amplitude, right?
It's a gradient of amplitude.
Yeah.
So.
Daniela Rizello says, thank you for a very nice presentation. Can you please indicate some strategy to determine model uncertainty? And that's a brilliant question.
That's a very good question. Model uncertainty is, and model uncertainty is difficult to get from these deterministic type schemes that a lot of us use. But I think that's also why when you're using these type of schemes, that's why it's important to run lots of inversions with different parameters and see what you get. There are some, you can get some estimates about that come from this linearized analysis that we do, but they're very restricted in model space. I mean, you really have to use a Bayesian approach to do that, I think, to get a really good, a proper indicator of the model uncertainty.
So NASA Mekbil has a question. Thanks, Randy, for this very informative talk. Looking at the last example you showed for Saba, the resistivity values vary between 0.8 and 10 ohms. I'm wondering how the response, the measured data of this very low variation.
I'm not quite sure I understand what the question is. It is true that in this area, these are low resistivity sedimentary layers. So I'm sorry, I'm not quite sure what's being asked.
Yeah, I think really NASA, I think you're asking about the error levels, right? And as Randy said, this is very high quality data. So the error makes it possible, the very low error makes it possible to determine resistivity variations.
Yeah, and don't forget we have controlled source EM data here as well.
Yeah,
so it's not just MT.
Yeah. Just for the audience's sake, Randy here used the other color scheme where resistive structures are red.
Well, thanks for pointing that out. I don't think about that. It's not always, we use red for the target, right? So here in this case, the red is the resistor. In the geothermal case, it was the conductive zone.
Yeah. Jerry Roth says, Randy, I enjoyed your enlightening talk as always. Further to Alan's comment about the quality of obtained fit, particularly for joint inversions, always advocate plotting the response from the computed inverse and directly compared with the observed data for local agreement, disagreement. So not a question, but a point.
No, but I think a very important point. And I think too often people treat inversion as a black box. They shovel data in and they get some number and, oh, right, well, we've got a solution. And I'm totally agree with Jerry and think that it's really important to, and I stressed earlier, you run lots of inversions, but I think it's important to look at not just a number, data misfit number, not to look just at a global number, but to actually make plots of the observed and predicted data. You learn a lot by doing that. So yes, I totally agree.
Yeah, which reminds me, one other point I wanted to make when you're talking about joint inversion, you showed those two minimizations and the overlap of the two.
Yes.
And I think for those of us who are doing a 2D MT only inversions, it's important to remember that that occurs already when we invert TE and TM together. That in fact you can get a TE minimization curve that's different from the TM minimization curve because TE and TM see the Earth differently. And
that's a very good point.
Yeah, when you do you jointly invert TE and TM, you're actually doing a formal joint inversion. The TE is mostly seeing currents and TM is mostly seeing charges on boundaries.
Yes.
Yeah.
Yep. Good point.
Ivan Granados says, what if the noise of the different data sets is variable at the different locations? The regularization parameters are still constant. Are the regularization parameters still constant in the whole region?
Well, I've left the whole business of regularization somewhat opaque here, and because again, I think a lot of that is part of the art form of an inversion, right? And you have, if you saw some of the inversion talks, like Doug's talk and Colin's talk, they showed how those parameters can affect the model, right? And so I think it's up to you, the interpreter, to put reasonable constraints on your inversion. And I guess that's more of a, I'm not quite sure what the question was, but I think that's a perfectly reasonable approach.
It all comes down to not only do we need good estimates of the estimator itself, but we need very good estimates of noise.
Yeah, and there's noise not just in the data, there's noise in our forward modeling as well. They're not, they're not completely accurate, and you have to understand the limitations of your modeling code.
We have a question from a Russian participant, and I'm afraid I can't read his name because it's written in Russian.
Pavel Alexandrov.
Oh, thank you. What are the prospects for solving inverse problems for anisotropic and bi-anisotropic media?
Well, we solve for anisotropic in the marine controlled CSEM world. It's you have to solve for the anisotropy because it's necessary. The geological, these finely layered sedimentary sections that we're in create an electrical anisotropy. We have to do that. And in fact, here, I was talking about the horizontal and vertical, but really it's more, in fact, like transverse tilted TTI, where it's really a long bed and perpendicular to the bedding. So in this case, it's absolutely necessary. In general, I think we have difficulty from magnetotelluric data by itself to determine anisotropy, except in some special cases. So does that answer the question?
I think so, yeah. Lars Lorenz says, thanks for the talk, Randy. Can you give an estimate of the amount of add-on time you would need to go from a standard CSEM inversion to a joint CSEM seismic structure inversion for the cross gradient approach? Time available is often a challenge due to CSEM being a latecomer in the project workflow.
So are we asking for doing, it's unclear if we're asking to do like joint CSEM and full waveform inversion? Is that maybe? No,
the question is asking how much longer, compared to doing a standard CSEM inversion, how much more time do you need to do the joint CSEM seismic structure inversion?
Well, it doesn't, it's the same. I mean, it's an additional, the coupling in the seismic information via the structure tensor, it's fixed, and it's just it's like a regularization term. in some sense. And so it doesn't really, it's not like it's not really a big additional, I mean, you're doing inversions anyway, right? See, it's true, CSEM is computationally intensive because you have lots of receivers, you have lots of frequencies and lots of data you have to simulate. If you do a single domain inversion and you want to do one with structured tensor, it doubles the time, basically. Yeah. So, not sure. I'm not sure if that's very satisfying or answers the question.
Okay, we'll just we better make this the last question because we're kind of over time. From Arvin Kapia, he says, "Hi Randy, thanks for this amazing presentation." And that's we all feel this, Randy. You mentioned about data weights, and we should think about the number of data points when deciding those weights. Care to speak a little on model weights and coupling weights, and how would one think about when deciding these values?
Well, the model weights, you know, I think a lot of what I said, a lot of the approaches are valid for data weights or model weights. I mean, Doug talked about L curve analysis, where you start with high values of the model trade-off parameters, and you run your inversion, and you carry, and then you can reduce, and you run lots of inversions, and you can trace out a curve, and you can see where it's not, you know, just you don't just look at the curve, but you look at the models as well and see where you're fitting the data reasonably and where you don't, before you start producing strange artifacts in the inversion. There are other schemes like Occam, right, that try to do that automatically, carry out a line search at each inversion iteration. I tend to fall in the camp. I like to fix a value and run an inversion and see what I get, because I think there's a lot of value in that, rather than have the code try to automatically adjust. But there are certainly approaches that some people have some sort of a cooling schedule that start at high values and reduce it throughout the course of the inversion, trying to get to a target misfit. So all valid approaches, and I don't think there's any right answer to that.
Great. Well, we'll thank you again, Randy, on behalf
Sorry,
of
Alan.
Yeah.
Alan, before we go, I would like to use my sort of position of power as a co-organizer for a comment and a question.
Of course.
Okay.
So the comment, because you have that sort of multi-objective slide up there. So I did this for my PhD thesis for MT and receiver functions, or MT and seismic data. So there are a couple of papers if you're interested.
I am. That's excellent. Thank you.
I think the problem is these approaches are extreme. I think they're extremely interesting, but they're computationally expensive, as you can imagine. So what I used was a genetic algorithm, and the extension to 3D, of course, then becomes highly problematic.
Right.
And then the question, so I'm become more interested, so you talked a lot about the structure. So I've become more interested in the relationship between the different properties. So is that something you look at when you do this sort of for commercial purposes as well, or are clients interested in that, or is it mostly about structures?
It's mostly about structures. I mean, because I think internally to exploration companies, they're more interested in the petrophysical approaches. And it's something that we certainly think about and talk about, but it's difficult, you know, in the type of work we do, to have that information and do it. But there's certainly interest in doing it, because that's really what their companies are interested in. They could honestly care less about the electrical conductivity. They want to know about the physical properties, right? Porosity and things like that. So I think that's great, Max. And you know, I think it's something everyone's looking at. It's a tough problem, and because you have to have you have to have some rock physics models to do that, and these are, you know.
Okay, I was actually thinking about the other way around, because from the cross gradient, I mean, I think Gallardo and Meju did that also in the first paper. Yes, you can make some cross plots and, you know, look at those and sort of infer petrophysics from that.
Yeah, I think so.
Yeah, anyway, yeah, very interesting talk, and thanks for that. Yeah.
But yes, in the long, I'm interested in what you did on this multi objective function minimization.
Sure.
Yeah, Max had an excellent supervisor.
The best.
That goes without saying.
It does. Right. Well, thanks again, Randy. It's brilliant. And well, this video will be up, everybody, on the EMinar page and also on YouTube within a couple of hours. And then Randy will send me a version of this PowerPoint that will be up again. So just to quickly remind everybody, we have next week, where is it? There we are. We have next week the presentation at the same time from Nadine Villette on talking about a career as a geophysicist. And so thanks everybody, and bye, and stay safe, and see you next week.
Thanks, Alan and Max. Bye.
Thanks.